Today we're going to talk about rates of change, which hopefully you can kind of remember that a rate of change, going back to Algebra 1, that's just a fancy way of saying slope. And specifically we're going to be looking at two different types of slopes today. We're going to be thinking about the slope of a secant line, that's going to be referred to as an average rate of change, the slope between 2 points on a graph, and then really what we're looking to get closer to understanding is how do I find the slope when you only have 1 point on a line, and that's called the slope of the tangent line, or the instantaneous rate of change. Later on, next time, we're going to actually call that the derivative also, and that's kind of the first half of calculus, is these instantaneous rates of change, the slope of the tangent line. So we're going to kind of baby step our way there today. We're going to start with secant lines. We know how to do the slope between 2 points, and then we're going to see how we can somehow compress that slope of the secant line having 2 points. We're going to see if we can compress those 2 points together, get it down to just one, and then end up finding a way to get the slope of a tangent line. How do I find the slope when I only have 1 point? So that's what we're kind of working towards today. This is like a little mini notes packet. It's kind of a bridge between the first one and then really the next one, which is going to start diving more in depth into the calculus. Let us go for it. You can pause the video right here and you can read this more in depth if you want. Just kind of keep in mind the tangent line slope, that's our goal for today. How do I find the slope of the line that just touches the graph at one spot? But we can't get there at first, so we're going to begin with the slope between 2 points, which is the slope of the secant line, and then we're going to hopefully see if we can connect the two dots and then get to the tangent line. Okay, so here we go. Slope of the secant line is the average rate of change. Average means over an interval, right? It's not necessarily always going to be the same exact thing, but that's what the average rate of change is. So again, you guys can go ahead and pause and read if you want. I'm not going to read to you because I think that's kind of boring. But go ahead and pause it, read the paragraphs if you want. But generally, the first idea that you're going to need to know and be familiar with as we work on these first couple of examples is right here. If you want to calculate the average speed of an object over a certain period of time, what you need to do to find the average speed is you need to figure out what's the change in the distance. How far does that object go? And then you need to divide it by the change in time. So how long was it traveling? Like if you travel 100 miles in 10 hours, you know your average speed would be 10 miles per hour, right? You just take the total distance, the change in the distance, and you divide it by that total time, the change in the time. So we know that speed is change in distance over the change in time. That's how we're going to find this average speed over an interval, and that's pretty much the same thing as our average rate of change, which is just the slope between 2 points. Okay, now going back to that car example, if you have that 10-hour journey and you cover 100 miles, you know your average speed was 10 miles per hour. But that doesn't mean you were going 10 miles per hour every single second of that journey. Sometimes you may have been going 12, other times you may have been going 16, sometimes maybe you were stuck at a red light and you were going 0, or maybe there was some idiot in traffic who was going super slow and you were only going like 4. But we know that instantaneous values don't always end up being the same thing for the whole interval as the average. So that's conceptually going to be the difference between this secant slope, average rate of change, and then the instantaneous slope, which is the slope of the tangent line, the instantaneous rate of change. So we're going to start with the secants, the average rates of change, slope with 2 points, which we should all know how to do, and then we're going to baby step our way towards getting the instantaneous rate of change, which is that slope when I only know 1 point, slope of the tangent line. Alrighty, let's do these examples. I think there's like 6 or 7 of them. We're going to try to fly through as fast as we can, and then we'll be done. Here we go. Experiments have shown that when a dense, solid object is near the surface of the Earth and it is dropped from rest, it will fall freely y feet during the first t seconds, such that the distance the object falls is modeled by this function f of t, where t is greater than 0. So it gives me the distance that the object has fallen, right? So that f is the distance function. A rock breaks loose from the top of a tall cliff. What is the average speed? So it wants average speed. That's the slope between 2 points. What is the average speed during the first 2 seconds of the fall? And then explain why this rate is positive, not negative. Always look for what is it that it wants me to spit back as the answer. Average speed, so it just wants the secant slope. And then it says first 2 seconds. So we would want the time interval to be from 0 to 2, right? First 2 seconds, starting at time equals 0, 2 seconds elapse, so from 0 to 2. Okay, let's go for it. Average speed, remember that formula from your previous page. That's the change in the distance. The distance function here was f, so I'm going to put change in distance, and then my distance function here was f over your change in time. So then here, and specifically, if we wanted the time value to be from 0 to 2, I would need the slope. So f of 2 minus f of 0 over 2 minus 0. Remember your slope formula going back to Algebra 1, y2 minus y1 over x2 minus x1. So you're just doing the change in the y's over the change in the x. Remember that painfully nerdy joke about my running team's name, Team Slope, rise over the run. Okay, here we go. Average speed. F of 2 minus f of 0 over 2 minus 0. That's great. We would just need the calculator. You plug in 2 to the function. 2 squared. Actually, you really don't need a calculator for this one. 2 squared is going to be 4. And then 4 times 16, I think, is 64. So again, how I got this was I took 2, plugged it into the function, spit you out 64. Plug in 0 to that function. You're going to get out 0. And then 2 minus 0, we'll just leave that for now. So here, this change in distance, it looks like the total distance that this thing travels is 64. And then the total time is 2. We can do this division, so we know the average speed is going to end up being 32. And then always pay attention to your units. You have distance over time, so you need the units for the distance, which is feet, and then the units for the time, which is seconds. So this average speed would be 32 feet per second. Remember, that doesn't guarantee that the rock is always going that fast, but on average, that's how fast it was going. Gravity is going to cause it to speed up, so it starts off going slower, and then as gravity acts on it, it's going to pick up speed. But that average rate of change, that average speed, that tells us over the interval, on average, it's going 32 feet per second. All right, and let's think about the second part to this question, which is why is this value positive and not negative? Because, Mr. Bell, this thing is falling down, right? And if the position is decreasing, why isn't the rate of change negative? Well, you have to always pay attention to what the function is modeling, right? This function doesn't tell you the vertical height of the rock. It just tells you the distance that the object has fallen, right? And if you take something and you drop it, the distance that it falls should only ever get bigger. Like, you don't drop a rock and then all of a sudden it goes upwards from your hand. That wouldn't make sense. If you drop an object and you're measuring the distance that it has fallen, of course that value should only be positive, right? So let's answer this. As time goes, the distance the rock has fallen is getting larger. Another term for getting larger, we could say, is increasing. So the rate of change, I'm going to abbreviate it. So the rate of change should be positive. Okay, so as the time goes on, the distance that the rock has fallen is getting larger. It's increasing because that distance, right, it's always going to be getting farther and farther and farther away from the starting point. It's not going to yo-yo back up and approach your starting point. It's just going to keep on getting farther and farther away. That distance is always going to keep increasing, so that rate of change should be positive. Okay, next one. Or I guess it's just part B. It says, an inflated balloon is tied to a small rock. The rock and the balloon are thrown into the air while the rock is moving its height in feet above the ground. Ooh, so be careful. Here this function is modeling the vertical height in relation to the ground. So that's different than what the previous example was. Anyways, the ground is modeled by the following equation as a function of time. So it gives me this function f of x, and that's the vertical height relative to the ground, where x is the time in seconds since the rock was released. I always like to go ahead and, if you see your units, you can go ahead and circle the units. That way, when you're looking on this final answer, you make sure you go back and you snag and you put appropriate units on your answer. Okay, part 1. What is the average speed of the rock during the first 3 seconds? That's easy. Here we go. Part 1. It wants the average speed and it wants from time 0 to 3. That would be the first 3 seconds. So you're going to need the change in the distance over your change in the time. You don't always have to write out all of these steps that I'm doing, but I'm just trying to help you guys through the video. So we're going to need f of 3 minus f of 0 over 3 minus 0. And again, that was from 0 to 3. So you need the slope of that graph, right? It's a parabola. It's going to open down, and then you'd want to try to find the slope of the 2 points on that line, or that parabola, at one of the points being at time equals 0, the other one being at time equals 3. Anyways, slope formula, not too bad. Okay, now just pretend like you have a calculator, or if you have a calculator, just go ahead and do the calculations. I'm going to go ahead, I guess we can do it on the screen also. I'm going to type that equation in. You could plug in 3 and you could get that value by hand, and you can plug in 0 and you could get that value by hand. I'm just going to plug in the calculator just to speed things up a little bit. We've got negative x squared plus 8x. Oops, that's not the x button. Delete, delete, delete. Plus 8x plus 2. I'm going to get out of there, and I'm going to go vars, not that one, vars, y1 at 3. So it looks like that value is 17. Plug in 0, that's easy. If you plug in 0, the answer is going to be 2. So it looks like here we're going to get 15 over 3. So it looks like the position, or the vertical height, at time equals 3, it looks like it's 17 feet above the ground. And then at time equals 0, it started 2 feet above the ground. Okay. And then here we go. If it started at 2 and it ended at 17, that means the change in the height, the amount that it gained, was 15. And then, of course, the 3 seconds elapsed. So here we go. We've got this average speed. We've got 5. Don't forget your units. Feet per second. Okay, part 2. What is the initial height of the rock as it's released into the air? How do we know? Well, we know the initial time is going to be time equals 0. Therefore, remember the 3 dots means therefore the initial height is going to be f of 0, which is 2 feet. We did that already, right? F of 0 is 2 feet, but otherwise just go back, plug in 0 into your function, and then you're going to be good to find the answer. All right, first 2, hopefully not too bad. Average rates of change, slope of the secant line, slope between 2 points. It's the same slope formula you've been doing way back when, since Algebra 1. Hopefully it's not a problem. All right, now let's kind of read this, and let's try to see if we can start gearing towards more of what we're really interested in, which is the slope of the tangent line. Okay, I'm not really going to read this to you. Again, you can always pause the video and read to you. I would probably recommend it, but it's okay. We've kind of already talked a little bit about it. Going back to that driving example, like here, if your average speed is 60 miles per hour over a specific time interval, here it looks like they're driving for 3/4 of an hour, 45 minutes, and then they cover the certain amount of distance, right? You can find your average speed pretty easily, but that doesn't mean that you're going that same miles per hour every single second along that journey. Like sometimes you're going faster, sometimes you're going slower, so on and so forth. And so how we actually find what that momentary, instantaneous rate of change is going to be is really what the first half of calculus is going to cover, which is a derivative. Today we're just calling it the instantaneous rate of change, aka the slope of the tangent line, the slope of the graph when you only have 1 point. Okay, so let us go for it. Here, we're going to estimate it. We really aren't going to get to the exact process until I think the next example or 2, but we're going to estimate it. So it says, going back to that rock example in part 2, estimate the speed of the rock at the instant where time equals 1.2 seconds, where the distance of the rock falls is modeled by that 16t squared function. Okay, great. So remember on the previous, when we were dealing with this previously, it actually gave us the interval. It said, okay, from time equals 0 to time equals 3. It gave me a very specific, here's the beginning interval, here's the end of the interval, find the slope between the two. Really now it just wants me to find the slope at the 1 point. How you can approximate it, right? We always know how to find the slope between 2 points. It's just your slope formula. So in order to estimate what this tangent slope is, the slope at 1 point, we are going to pick a second point on the graph, and we're going to want that second point to be pretty darn close to that first one, and then we are going to do the secant slope between those 2 points, and then that's going to be an approximation. right? So luckily, we're just estimating it. We will be able to find this instantaneous value very soon, but here we're going to learn how to approximate that tangent slope. And you approximate the tangent slope by doing a secant slope. So let's go ahead and use time equals, how about 1.2? Let's make the second time really close. Here, I'll call this one T1. We'll call this one T2. Let's do 0, 0, 0, 0, 1. Like that t value is very close to the one that I'm starting. It's definitely not the same. It's different. These two values are different. The space in between them is not very big, right? Those points are very close together. But since these two are not the exact same, right? They're two different points. I can find the secant slope between these 2 points, but since those 2 points are so close together, it's almost going to be like having just the 1 point. It's still 2, so it's still just an approximation for what that slope would be at the one instantaneous point, but it's probably a good approximation. If you only did 1.21, and then you use the slope between those 2 points, you would get a decent approximation, because those two are fairly close. But the closer these two t values are together, the better your approximation is going to be. Like if you used 1.2 to time equals 7, like yes, that would be 2 points. You could find an average rate of change over that interval, but that average rate of change isn't necessarily going to be a good approximation of the instantaneous rate because that average covered such a long time interval. So if you want to approximate the tangent slope, you want to approximate that instantaneous rate of change, you're going to use the best secant line that you can. Of course, we could have added in some more zeros, but at a certain point, you're going to be all right. All right, so let's go. Speed is the change in distance over your change in time. And so here we're going to use these two time values. So I'm going to have f of 1.2, 1, 2, 3, 4 zeros, minus f of 1.2 over 1.2, 0, 0, 0, 0, 1, minus 1.2. So we're still using a secant slope. We're just using a very small secant slope since those 2 points are very near to each other. I guess this one, the first example was time interval 0 to 2. That was the rock with the balloon. That was 0 to 3. Anyways, whatever. So we got it typed in, 16x squared. Let's go ahead and get out of there. And I'm just going to type this straight in. Here we go. Watch how I do it. I'm going to do vars. Let's see. Vars, y vars, y1. I'm going to tell it to evaluate at 1.2000001. And then I'm just going to do minus vars, y vars, and then tell it to do 1.2. So I'm basically doing the whole numerator right now, and you get a very small number, right? And then here I'm just going to divide that by, open a parentheses, because you don't want to mess up your order of operations. You want to divide by the whole entire denominator. So I'm going to divide it by 1.2000001 minus 1.2. You could have done it all at one line. I usually will at least break it down into two. But here we find that that secant slope between these 2 points that are very close together, that secant slope, we'll call it 38.4 feet per second. Now be careful with your notation. Remember, this question asked me to approximate or to estimate the instantaneous speed. Here, that's still the average speed. It's the average speed from this really small interval. Right? It's the average speed between those two very close together t values, but that's still just a secant slope. We would want to say, therefore, the instantaneous speed at time equals 1.2, and instead of an equal sign, right? If you're saying average speed equals, yes, because all of that is the secant line, right? The average speed is exactly equal to that value, but that means your instantaneous speed, that slope of the tangent line, that would just be at 1 point. You're going to need to put the approximation symbol, so 38.4. feet per second. Again, it's kind of nitpicky, but just be careful. The secant line between these 2 points, the secant line is this number. That means the tangent slope is about that number. It's probably a very good estimate since those 2 points were very close together, but you would still want to make sure you put the approximation squiggles because it was an estimate. Okay, now you guys can go ahead and pause and read this if you want. I'm going to go ahead and draw a diagram, and then we're going to kind of talk about conceptually what is happening here. But again, I don't like to just read things to you all the time. I want to go ahead and just, you can pause the video or you can just listen to me ramble as you do it. But yeah, I like to kind of go a little bit off the beaten path. I guess I could just change the notes because, like, they're my notes. I could change them, but I'm just lazy. I'm just going to supplement the notes here, right? So the idea is we don't want to just have to estimate these tangent slopes. We want to actually be able to find the precise values for them. So here, let's go ahead and conceptually think about it. Right, this slope, if I have these 2 points, I'll just call this some random function f of x. I draw parabolas because I'm a terrible drawer, and I know that is something I can do at least quasi-decently. If I wanted to find the slope of that first dotted line, right, that line is going to hit the function 2 different places. So that's a secant line, and I could find the slope between these 2 points. Now let's label this first point as x, and let's call the gap in between these 2 points h, right? We're just kind of making them arbitrary values right now. But we'll call this first point x, and then this gap in between the 2 points, we'll call that h. So then that second point right here, that second x value, that would be x plus h. If that value is x, and that segment length is h, then that total value, segment addition back from geometry, is x plus h. Okay, now the y values, here you'd have f of x, and then over here, you have f of x plus h. And then I could still find the secant slope in between these 2 things. Let me zoom it out so I can write a little bit underneath it. So this secant slope, right, which is your average, that's a terrible average, your average rate of change. You could do that by just doing your slope formula. It would be y2, so we'd have f of x plus h minus y1 over x2 minus x1. All right, that is this expression right here. That is mathematically going to tell you what the slope of that secant line is. But I don't want to have the slope between 2 points. What I really want is to somehow just find the slope of this line, right? If it's just going to touch the function at that 1 point, graze it, and then go on its merry way, how would I find the slope of this tangent line, right? So the dotted one was the secant, and then here, this more terribly drawn line is the tangent. How do I find the slope when there's only 1 point? Because you can't use the slope formula if you only have 1 point. Well, you kind of can, but you have to take a limit for it, right? Conceptually, here's what we're going to do. We're going to take that secant line, that dotted line, and instead of having the 2 points, we are going to compress those 2 points together. We're going to shrink that gap down to 0, and then we're going to turn that secant into a tangent. And how we do that is through a limit. Again, remember, this f of x plus h minus f of x. By the way, let's look at what happens. You have x, f of x plus h, minus f of x. Here you have x plus h minus x. Those x's in the denominator, they're going to cancel, right? So this is actually called the difference quotient. And you should have seen it last year in pre-cal, at least if you were in the pre-AP or the advanced pre-cal. You should have seen something like this last year, and you probably hated it, but that's very useful. It's just the slope between 2 points, right? This is a secant slope, y2 minus y1 over x2 minus x1. It's just the secant slope between these 2 arbitrary points with the gap in between those points being h, right? So here is your secant slope. Now what we're going to do is compress those 2 points together, and we're going to turn that secant into a tangent. And how you're going to accomplish that is through a limit. If I take the limit as h goes to 0, right, h is that gap in between the 2, if h gets closer and closer and closer and closer to 0, that gap shrinks and eventually goes away, that's going to compress the 2 points into just 1, and then that is how you end up getting the tangent slope, which is your instantaneous rate of change. So it's a little bit weird. You have to do the difference quotient. Remember, that by itself is the secant slope, the slope between 2 points, but then actually going through this limit process and shrinking the gap down to 0, that is how you turn the secant into a tangent. That's how you compress from 2 points down to just 1. right? So this right here is your formula. That's the formal definition of a derivative. We'll get more into that D word next time, but this is how you find the slope of the tangent line, aka the instantaneous rate of change, aka next time, the derivative. Okay, so let us get back into these notes. Here it has, instead of x, it has a, because it's already got your value having been plugged in. Wonderful. Okay, let's go ahead and let us get into this example. So now let's go back and let's not approximate the instantaneous speed anymore. Like, let's actually find what that precise instantaneous speed is at time equals 1. Okay, and to do that, we're going to have to use this limit process. So let us go for it. Okay, so this instantaneous speed, remember, you're going to do the limit as h is approaching 0, and you're going to have, here, let's go, I'm not going to plug in the 1 yet. I'm going to wait, and I'm going to plug in the 1 later. So I'm going to have f of x plus h minus f of x over h, and then of course as h goes 0. There's your formula. Let's start plugging some stuff in. So you have the limit as h is going to 0. Remember, you need to carry this limit notation until you go through and you evaluate it. Until you change the h's to zeros, you need to keep writing that notation or you're going to lose points. Right? But here I'm going to take the function, and then everywhere I see a t, oops, sorry, instead of t's, I used x's. It doesn't really matter. T's, x's, potato, potato, whatever. It just represents your independent variable. I just happened to use x because I forgot the question was in t's. Oops, sorry. But here, instead of the t, we're going to plug in t plus h, or I'm going to use x plus h. So here we have 16 x plus h squared, right? You take that function and then you evaluate it with x plus h. So that means you would take this and plug it in anywhere you see the variable in your function. And then I just need to subtract f of x. So that was just 16x squared, and then divide it by h. Cool. Let's simplify. If you FOIL this out, you're going to get x squared plus 2xh plus h squared minus 16x x squared over h. You're going to need to distribute the 16. Am I still on the screen? It looks like it. Let me scroll up a little bit. So I have 16x squared plus 32xh plus 16h squared minus 16x squared. Now, if you had tried to evaluate it, if you had tried to plug in the 0 at any point really up until now, you would have gotten a 0 over 0. You would have gotten that weird indeterminate form. So you have to do the algebra. You've got to kind of expand it, see what cancels, see what reduces, and then after you've done all of that algebra, then you'll be able to get this answer. Here you can see the 16x squared and then the negative 16x squared. Those are going to cancel. That's really nice. Anytime you're doing this difference quotient work, all of the non-h terms should always and will always cancel, right? Because you're going to need to, before I can plug in the h is 0, you're somehow going to need to get rid of this h in the denominator, which means you're going to have to take everything in the numerator and then divide it all by h. That's how that h is going to go away. But you can't divide by h if some of the terms in the top don't have h's. But luckily, if you do all of the algebra correctly, all of the non-h terms, here I had the 16x squared and then I had the negative 16h terms, they should always and will always cancel, assuming you've done the algebra correctly, right? And then what you could do next is factor out the h. You don't really have to. If you can kind of just see like, hey, I'm going to cancel 1h here, 1h here, 1h here, right? You're going to cancel the h in the denominator, and then also to keep it balanced, you're going to reduce every single term in the numerator also by 1h, right? It's not just this one and that one that cancel. You'd have to reduce that from h squared down to h. But you could also factor out an h and then reduce it. But I don't really want to. That's just kind of a waste of time, right? So I'm going to cancel the 1h, which means every single term in the top is also going to get reduced by 1h. And so here, let's regroup everything that we still have. I've got the 32x plus the 16h. And then now that I've reduced it, right, the non-h terms canceled, leaving me stuff in the top, but everything in the top had at least 1h, so I could reduce everything by the h. Now I can go ahead and I can evaluate it, 32x plus 16 times 0, so that's going to cancel. So I'm going to get this formula 32x. That is what's called the derivative formula, right? And how you're going to see that written is y prime. It's the instantaneous rate of change formula. That's going to tell me, how do I find the instantaneous rate of change? How do I find that slope of the tangent line? How do I find that derivative at any instantaneous value, at any singular point? And then the very last thing you would have to do is plug in the t value, or here plug in the x value that you want. So at time equals 1, you can just plug it in, right? We want that derivative formula at time equals 1. And we're going to end up getting 32. And then don't forget your units. This one was feet per second. Okay, so it's just better to save that x value. At some point, you're going to have to plug in 1. You can plug it in at the very beginning. If you plug it in at the very beginning, you should still get that same answer. Here I worked it with the 1 having been plugged in. Again, you can pause it if you want to watch all or kind of work all the way through this, but you don't have to. If you plug in the 1 at the beginning, it'll work and it'll still jump you to the answer. But it jumps you straight to the answer, right? You get straight to the 32, which is only that one specific singular moment of time. What's really nice, if I kind of leave the t's, or if I leave the x's in there, I actually get that whole derivative function. I get this formula at the end. And then from that formula, I can plug in the t value or the x value, and then I can get the answer. Now, it doesn't really matter whether you plug in the 1 at the beginning or whether you plug it in at the end if there's only one part. But let's flip this over, and then let's see this next one, right? It says, now find the speed at the instant time equals 1.5. So if you had done it this way, where if you plug in the t value right at the beginning, right, if you plug in 1, you're only going to get that one specific instantaneous speed value, right, the speed at time equals 1. So if you only got that one value, and now you wanted to do a second one, well, you would have to redo this whole entire limit process, and you'd have a whole long question to, again, do all that limit work. Right, so that's why it's not really super great to plug in the x value or to plug in the t value at the beginning. You can, it will give you the right answer, but it only gives you that one right answer. What's really nice about leaving the x's in or leaving the t's in is that at the very end, you have this formula that still has x's, and then this formula you could use at whatever times you want. So I'm just going to copy this over, right? I'm not going to redo the work. We've already done the derivative, that limit of the difference quotient stuff. So I already know that this formula was 32x, or if you wanted to go back, it'd be 32t's if you're working with t's. And then now, if I wanted it at time equals 1.5, all I would have to do is 32 times 1.5, which is 48 feet per second. So that limit work is long, and it's not super enjoyable. If you plug in the t value or the x value right at the beginning, you're going to get the right answer, but you only get that one answer. If you leave the x's in there or you leave the t's in there, you get this whole function. And then you can plug in all sorts of different values. Like if I wanted the speed at 5, okay, 32 times 5. If you wanted the speed at time equals 10, okay, 32 times 10, right? However, if you did all of those different instantaneous speeds by plugging them in initially, you'd have to redo a brand new limit every single time, which is not preferable. I don't recommend it. You'll get the right answer, and I guess it's good algebra practice, but it's just so much more efficient. Leave the x's in there so you get the function, and then from this function, you can plug in as many different x values as you need, and it's pretty quick, pretty easy to get the answer. Okay, 2 more examples. We are making progress. Here we go. Mass on a spring. A mass is bouncing up and down on a vertical spring, or a vertical, bouncing up and down. I can't read. On a spring hanging from the ceiling. Its distance, y, from centimeters, so we've got centimeters, and it's the distance from the ceiling is measured by strobe photography each 1/10 of a second. There's your units for your time. The table lists some seconds and distances. Part A, how fast is the mass moving? At time equals 0.3 seconds. So it wants that instantaneous speed, and it wants at time equals 0.6. So it wants 2 different instantaneous speeds, right? It wants 2 different instantaneous rates of change. It wants 2 tangent slopes. And then part B, what direction, either up or down, is the mass moving at those respective times? Explain your reasoning. Okay, let's read these notes that I put. Important concept. Even though this question asks for the instantaneous rate, there's no way to calculate that instantaneous rate for this question. Because remember, to find the instantaneous rate, you would have to do this. You would need to do the difference quotient, and then you'd have to take the limit of it, right? You'd have to do all of that limit work. But in order to do that, you have to know what the function is, right? You have to plug in the function here, then you have to take the function and then plug in x plus h, and then that goes in your top left chunk. But you can't do all the limit work if you don't know the equation for the function. Here, all I know is some data points from the function, which I guess if you typed them into the calculator, you could do some type of regression, and then you could approximate what that function is. But then all you still have is an approximation. And we already know we have a much easier way to approximate an instantaneous rate. We can do that by just doing an average rate, and specifically the best average rate possible. Okay, so this problem asks about the speed specifically at time equals 0.3. We are going to go ahead and try to pick 2 points around that specific time. We're going to do the average rate, the secant slope, between those 2 points, and then that average rate, again, is going to be the approximation for the instantaneous rate. Now, here's an important concept. Let me, again, just draw a parabola. And let's say I've got, how about 1, 2, 3 points. And I don't know, we'll just call them 1, 2, 3. Let's say the goal is to end up finding what that tangent slope is. I don't know, I just make the line bigger, make the dots bigger, and then it looks like everything's touching. How wonderful. Right, let's say the goal is to find the slope of that tangent line. And we're trying to figure out which secant line is going to give me the best approximation. Well, there's a couple of different options, right? If we want the tangent line at x equals 2, we could do the secant from, how about 1 to 2? We could do this secant. I guess x from 1 to 2. Sorry, my handwriting is just getting terrible. Oh well. But, you know, the problem, if you want the tangent line at 2, and if you use the secant line from 1 to 2, remember, we're trying to get these two things to have as close to being the same slope as possible. And from geometry, you should remember that if two lines have the same slope, or very near to the same slope, we would want them to be parallel, or as close to parallel as possible. But if I use the tangent at 2, and if I use the secant from 1 to 2, well, both of those lines go through this point. So those lines are going to intersect. And I know lines that intersect aren't parallel and probably aren't even very close to being parallel. So I'm thinking that's probably not the best secant line to use. But let's try 2 to 3, right? Let's try the other one. So if I did this secant line, and that's x from 2 to 3. Again, you're going to hit that same issue. Here is your tangent slope. That's what you desire to have. We're going to approximate it with this secant slope. Now, that tangent and that secant, they're not too far off. Like, at least they're both positive numbers. But again, that red line, that's going to intersect with that tangent line, the one that I have in the pencil. So again, that's really not the best approximation for us. The secant from 1 to 2, or the secant from 2 to 3, neither of those is going to give you the best approximation for the tangent at 2. But there's one more option, and that would be the secant from 1 to 3. Like, hey, if I'm investigating the instantaneous at 2, let's try to actually ignore that point. We'll use the closest on the left and the closest on the right, and then let's investigate that secant from 1 to 3. Now again, the tangent that we really want and the secant that we are going to approximate it by, they're probably not going to be precisely parallel. But that secant, when you kind of ignore the value and you use the closest on the left and that closest point on the right, the one where you kind of skip over the one that you're investigating, that secant is much better than either of the other two options. So an important conceptual idea here. We can approximate a tangent by doing a secant, but we want the best approximation possible. And if I wanted to approximate the tangent at 2, you would not use 2 for your secant line. You would use the closest point to 2 that you know on the left, and the closest point to 2 that you know on the right, and then you would use the secant between those 2 other points as a way to make the approximation. Right? So here we go. If we want to approximate the instantaneous at time equals 0.3. So I'm not going to use 0.3. Instead, I actually want to use the secant from 0.2, which is the closest on the left, to 0.4. You don't use that value that you're investigating. Let's use 0.2 to 0.4. Okay, so here we go. The average speed. Remember that we would have y of 0.4 minus y of 0.2 over 0.4 minus 0.2. Y of 0.4, let's go get that from the table, 7.37. Y of 0.2, 3.99. Do the subtraction, type it in with your calculator, and you're going to end up getting 16.9. So then I could say, therefore, my instantaneous speed at time equals 0.3 is not equal. The average is equal, right? Because that's what the secant line is. But here, this tangent is going to be about 16.9, and then don't forget your units. We had, I think, centimeters per second. Okay, part B. It says we're going to approximate that instantaneous at 0.6. So we're going to use, I think, not 0.6. We're going to use the 0.5 to the 0.7. So it's the closest on the left, the closest to the right. Don't do this secant. Don't do that secant. Those will give you okay approximations, but remember, that line and that line would both intersect with the tangent at this point. But if you think about the secant from this to this, it's probably going to give you the best approximation. So from 0.5 to 0.7. So just redo this same work, but instead of 4 and 2, use 7 and 5. So average speed, y of 0.7 minus y of 0.5. Snag those values. You have 6.1 or 6.01 minus 8 over 0.7 minus 0.5. Type it into your calculator. You end up getting negative 9.95. So therefore, the instantaneous speed, am I still on the screen? Yep. Instantaneous speed at time equals 0.6 is going to be about negative 9.95 centimeters per second. Well, I guess that's still all part A. That's just part A. That's just, I guess. No, I guess, yeah. That's still all part A. Part B is deciding whether they're moving up or whether they're moving down. And this one's going to be a little bit weird, because usually positive means going up, negative means going down. But again, you need to be careful and pay attention to what is this question, what is this function in this question actually modeling. And this function, it tells us it's measuring the distance from the ceiling. So think about it. This first one, 16.9, that means at that time, you're gaining about 16.9 centimeters per second. So you have this ceiling, right? And if you're gaining 16.9, right, the distance is getting bigger. And if everything is in relation to the ceiling, right, if the distance from the ceiling to that box, if that distance is increasing, the box is actually moving downwards, right? Usually positive means going up, negative means going down, because usually we are measuring distances in reference to the ground. Here we're using the distance in reference to the ceiling. So since distance to ceiling is increasing, remember the positive rate means it's increasing, you are moving downwards. Weird. Positive means down because that means the distance from the ceiling is getting bigger, right? Positive means increasing, which means getting bigger. And if the distance from the ceiling is getting bigger, that means you're moving downwards. And then the other one for here, we got the distance to the ceiling is decreasing, right? It means at this time value, 0.6, it looks like that distance from the ceiling to your box, that distance is losing about 10 centimeters each second. And if your distance is getting smaller, that means the box is actually moving upwards. Sorry, I'm kind of running out of room, so it got a little sloppy there at the end. So just be careful. Positive usually means going up. Negative usually means going down, because usually everything's in reference to the ground. Here things are in reference to the ceiling, so everything's just reversed. All right, last example, then we're done. Okay, a door has an automatic open-close operation. When someone pushes on the door, it opens fast at first, slows down a bit, stops in the fully open position, starts closing quickly, and then finally shuts slowly. It's a weird door. It's like, it's weird. I don't know. It's weird. I hope you appreciated the sound effects too. I thought they were top-notch. Anyways, as the door moves, the number of degrees it is open or from the closed position depends on the number of seconds it has been since it was pushed open. The door is first pushed open at time equals 0, and it's closed again at 7 seconds. So the whole cycle takes 7 seconds, right? To open and then close, whole thing takes 7 seconds. And then it gives us the function d. Okay, great. And remember, it's going to be degrees is the unit for really how open it is, and then the time is in seconds. Wonderful. Part A. The door is fully open from the closed position in 1.443 seconds. What is the average speed in degrees per second? Look at that. It even tells you what the units need to be at the end. How lovely. What is the average speed that the door swings from closed to fully open? So remember, it starts at time equals 0, starts closed, and then it tells me it's fully open at 1.443. And if it wants the average speed, average is the secant slope, which is 2 points. So here for part A, really easy. It just wants the average speed. So I'm going to do the change in the degrees over the change in the time. So I need the degrees at that final time, like when it's fully open, and then minus the initial degrees, and then over the time that elapses. Do not assume that this door opens 90 degrees, or don't assume that it's going to open 180 degrees, right? We don't necessarily know that, and also don't assume that that's 0, right? You actually have to plug it in. I hope the door is going to be an angle of 0 at time equals 0, because otherwise that store may maybe get robbed or something. But don't assume anything about, hey, is this 90 or is this 180? No, just plug it in and then figure out mathematically what that fully open position is. I'm not going to bother typing it in, right? Just kind of envision me typing in with the calculator. I have my notes key. I already know what the answer is going to be, so I'm just going to go ahead and jump straight to them. If you were to type this function into your calculator and then plug this number into it, you would get 106.14757. So it looks like that fully open position is about 106 degrees, right? So not 90, not 180, okay, whatever. And then the initial position is 0. Right? If you plug in 0, it's going to kill. And then here, if you do the division, right, really those cancel, they go away. If you do this divided by this, you're going to end up getting 73.56, and we'll call it degrees per second. That's the average kind of rate of opening. Remember, sometimes it opens quicker, and then it kind of finishes opening slowly, so it's not always opening at that specific kind of speed. But that's on average how it opens. Part B, estimate the instantaneous rate at time equals 3 by using 3.00001 for the second time. That's really good. I got worried there for a second. If it said find the exact instantaneous rate, right? If it wanted the tangent slope of this function at time equals 3, remember, to find the exact tangent slope, you would have to do this difference quotient limit work, which would not be fun for a function like that. But thankfully, it doesn't want us to get the exact tangent slope. It just says approximate that tangent slope. So we're going to approximate that tangent with the secant, and then specifically it tells me which secant to use. Remember, the closer those 2 points are together, the better your secant is going to approximate your tangent. All right, so here we go. Instantaneous at time equals 3. We're going to approximate it by doing the average from 3 to 3.1234. So here we go. We got D of 3.00001 minus D of 3 over 3.00001 minus 3. we are approximating the instantaneous by doing a pretty good average, right? And the better, the closer those 2 points are together, the better your estimation is going to be. If you plug that into your formula, you're going to end up getting, let's see, 74.99973 minus 75 over, if you do this subtraction, it's 0.00001, and then you end up getting negative 27 degrees per second. I think it's like 26.986, but we're estimating anyway, so whatever, I don't care. Usually 3 decimals is what I want. Here I'm just going to round it to 27. Okay, so we got the 2 average rates. That one it asked for an average, that was great. Here it asked for the instantaneous, but it told us to just use the average, and that was really good. It even specified which 2 points of the secants to use. And then the last thing, explain what is happening with this door for a rate that's negative. So here, right, if you think about that door is opening, that door is gaining 73.56 degrees every second, right, on average. It's not always increasing at that rate, but on average, right? The positive means you are gaining degrees, so it would be opening. So that means here at time equals 3, right, you're losing approximately 27 degrees each second. So if your angle is losing degrees, that means the door would be closing. Right, so negative rate means the angle is decreasing. Therefore, the door must be closing. Boom, that's it. Let me flip it over and look at this last page just really quickly. This just has some miscellaneous stuff for you. Again, I would probably recommend you just hit pause on this video, skim through it, but really, we're going to work through all this stuff. Really, the only thing that's like critically important here, right? Remember your limit notation, right? When you're doing that tangent slope stuff, you need to carry that limit notation. Don't drop it until you plug it in, but you need to do that limit work if it's wanting you to find the exact instantaneous rate. If you do the secant, that's going to give you an approximation. You could get a really good approximation, but a really good approximation is, wait for it, still an approximation. The only way you can get it exact is to compress the 2 points into the 1, send the gap down between them into 0, take the 2, compress it to 1, turn the secant into the tangent. So without the limit work, you cannot get the exact instantaneous rate, right? The slope of the tangent. And then the other one, here I guess just know, remember speed should always be positive. Velocity is a vector. Velocity could be positive, it could be negative. But if you're ever confused about the two, remember speed is just the size. It's the magnitude of the velocity. So if your velocity is something like 35, negative 35, that means like you're going 35 miles per hour, but maybe like downwards or south or whatever the negative means in relation to that direction. Okay, that's about it for now. I'll see you next time.